I'd like to thank the organizers for giving me an opportunity to talk here, as well as for giving me a chance to stay at the City Hotel, which is very comfortable. I enjoy. So, as in the title, my talk concerns multiple weight varieties. But what is multiple weight varieties? A multiple weight variety is a symplectic quotient of a direct product of several coadjoint orbits of a compact Lie group G with respect to the diagonal action of the maximal torus. Its geometry and the topology are closely related to the combinatorics concerned with the weight space decompositions of a tensor product of irreducible representations of G. Here is a short history. Weight varieties, which means that the number of coadjoint orbit is just one, have been studied, for example, in Hu, Gilman-Raman, Sternberg, Knutson, Golding, and so on. And double weight varieties, which means that the number of coadjoint orbits is 2. For the special case, G is SU3, was studied by Suzuki in 2013. And in our approach, vector partition functions with weights or with multiplicities and the associated volume functions are very important. So in this talk, we consider the case that G is of type A, like SU3 or SUL plus 1, and study special kinds of multiple weight varieties. Okay, so let me start by recording some basic properties of coadjoint orbits or Frag manifolds. So G is going to be a compact Lie group such that simply connected and rank L. In our main example here is G is SUL plus 1 of type AL. So as you know, G acts on the Lie algebra G here by the adjoint action. Also, G acts on the dual of G star by the coadjoint action. So by definition, a G orbit in G star, the dual of G is called a coadjoint orbit. Here are some notations, and denoted by T, a maximal torus of G, W, the while group, and T star is the dual of the Lie algebra of T, and T star plus is the while chamber, where lambda 1 and lambda L is the fundamental weight of this root system. And we also denote by T star plus plus the interior of the while chamber. And similarly, let P be the weight lattice generated by the fundamental weights, and denote by P plus the set of dominant weights, and P plus plus will be the set of regular dominant weights, like this. So, as usual, we identify G with G star by means of some invariant in the product of G, and we regard T star plus, the positive while chamber, as a subset of G star. And then the intersection of each coadjoint orbit with T star plus the while chamber is just 1 point. So, for lambda in the while chamber, the coadjoint orbit through lambda is denoted by O lambda. Okay. Now, if lambda is in the interior T star plus plus of the while chamber, then, as you know, O lambda, our coadjoint orbit O lambda, is diffeomorphic to the complete Frag manifold G over T. Otherwise, O lambda, coadjoint orbit O lambda, is diffeomorphic to partial Frag manifold G over U, where U is the centralizer of a torus in G. For example, if G is A1, that is SU2, then coadjoint orbits P1 or just one point. Point is orbit's origin. And if G is SU3 of type A2, then O lambda is SU3 over T2 or P2 or just one point. In general, if G is of type AL, then coadjoint orbits are described. Coadjoint orbits are identified with a homogeneous space like this. L plus 1 over this subgroup, the product of sub-unitary groups. Okay, so which include projective spaces, Grassmannians, and so on. And it is very well known that O lambda is a Kähler manifold, and actually a projective variety. So the canonical symplectic form, denoted by omega lambda, is given by this formula, KKS symplectic form, and the complex structure compatible with this symplectic form is given by this description of O lambda as a homogeneous spaces, GC over P minus or GC over P minus, where GC is a complexification of G and V is a Borel subgroup and P is a parabolic subgroup. Okay, next I want to remind you the relation to representation theory of G with our coadjoint orbit. So let lambda is in the dominant weights, and let V lambda be the irreducible representation of G with highest weight lambda. Then the famous Borel-Weill theorem said that we have the isomorphism like this, where L lambda is a naturally defined harmonic line bundle over O lambda, such that the C1 is represented by this Kähler form, and H0 is of course the space of harmonic sections of this line bundle. In fact, O lambda, our coadjoint orbit as a project variety, is described by in this form, which means that O lambda is a projective variety associated with this graded algebra, where K runs through positive non-negative integers. K is multiplied to lambda. And this description means that the topology and geometry of the coadjoint orbit might be controlled by representation theory of G. And moreover, Lefschetz's fixed point formula, as you know, for the action of T on O lambda and L lambda correspond to the Weil character formula for the irreducible V lambda, which takes the form in this form. Okay. Okay, so let me introduce the notion of multiplicity variety and multiple weight variety. So let lambda 1, lambda 2, and lambda n be in the Weil chamber and mu is in T star. The space Mg or Mg of lambda is the quotient by G of the subset in the direct product of coadjoint orbits defined by this equation. The sum of xi's is 0. Okay, this is the definition of Mg. And similarly, Mt of lambda mu is defined by the quotient by T of the subset defined by this equation in the product of coadjoint orbits, where P is a projection from K star to T star, and G acts diagonally on the direct product of coadjoint orbits. So both are called multiplicity varieties, as which reason is I will talk later. And especially MT is also called a multiple weight variety. This is a space I consider in this talk. Okay, suppose our lambda 1 and lambda n in the lambda 1 and lambda n are dominant weights, and mu sits in the weight lattice. In this case, mg or mt is a projective variety associated to this graded algebra. Mg is a proj of this algebra, mt is proj of this algebra, where the summand here is the space of invariance in this tensor product, where k is non-negative integers. Also, the summand here is a weight space of weight k mu in this tensor product. Okay. Again, as in the case of coadjoint orbit or flag manifold, this means that the topology and the geometry of mg or mt might be controlled by representation theory of G. Okay, so it is natural to consider the following quantities. Namely, we define Qg of lambda to be the dimension of the space of invariance in this tensor product. This is the definition of Qg of lambda. And Vg of lambda is the asymptotics of this Qg. Namely, we put k non-negative integer here and divide by this number, this complex dimension of the mg, and take the limit. This is the definition of a Vg of lambda. And similarly, we define Qt of lambda mu is to be the dimension of this weight space. Weight space with weight mu in this tensor product, and Vt lambda mu is its asymptotics. Actually, this is a combinatorial object, but they correspond to characteristic numbers of mg or mt by the following theorem. This is a combination of famous theorem due to Guillemin-Sternberg, Borel-Bay, and Riemann-Roch. But we assume some smoothness conditions, and that conditions, the Riemann-Roch index and symplectic volume of mg or mt are given by the quantities above. Actually, mg Riemann-Roch index of mg is just this number, integer, and volume of mg is given by this asymptotics. Similarly, and Riemann-Roch of mt is given by this Qt lambda mu, and the volume is just Vt lambda mu defined here. So it has a topological geometrical meaning like this. What's up? Okay. I think it's okay. Okay. So next, I want to explain the section pairings of mg or mt. So let this time lambda 1, lambda 2, lambda n is in lambda n in the wild chamber, and mu is in T star, and we write each lambda I or mu as linear combinations of the fundamental weights, and Pij or Xi are coefficients in this linear combination. Then we can see that the symplectic forms omega g, omega t of omega g or omega t become this form, where Pij appearing here or here, and Xij are just the coefficients described above, and Zij prime here, 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 or gamma j appearing here are the closed two forms which correspond to the fundamental weight lambda j. Hence, by definition of the symplectic volume, we have the following proposition. Namely, a volume of mg, defined by this formula, is a polynomial of the coefficients in this expression of Pij, which is a generating function of intersection pairings in this form. The product of some Zij's and integrated over mg. Similarly, the symplectic volume of mt is defined like this, is a polynomial of Pij appearing here and Xj appearing here, which is a generating function of intersection pairings of mt, like this form. Okay. So the symplectic volume of M is mg or mt, contains much information of the homology ring of M. In particular, we have the following about mt, multiple weight variety. So let G is SUL plus 1 of type AL, and suppose that here is the assumption, suppose that each coadjoint orbit lambda j has a topological type of this homogeneous space, namely UL plus 1 over this form, some products of U1 factors, several U1 factors, and another factors. Then we can show that the homology ring of MT is generated by Zij and gamma k multiplicatively. Zij and gamma k appeared here. Okay. The homology ring of MT is generated by Zij and gamma k multiplicatively. Hence, if we can find an explicit formula for a volume of MT, which should be a polynomial of gamma ij, Pij and xk, then we can know all the intersection pairings of MT because of the previous proposition. Here, if you know about this volume very completely, then we can get the information of these intersection pairings. And in principle, all the intersection pairings of MT recover the ring structure of real or rational homology of MT in principle. So the volume is very useful invariant in our setting. Okay, next I want to go to some examples. So let me consider multiple weight variety of type A and of special kind. So let G in this section, let G is SUL plus 1 of type A, and lambda 1, lambda n is in the interior. For simplicity, we assume that lambda 1, lambda 2, and lambda n sits in the interior of the Weyl chamber and mu is in T star. And consider the multiple weight variety defined in this form. Now, first, consider the image of the projection from the product of quadrant orbits to T star. The image is, it is well known that it is a convex polytope. Here are some pictures. This is the case, G is SU3 of type A2, and N is 2. You see, the projection of the product of coadjoint orbits to the dual of T star is something like this, convex polytopes. And connected component of the set of regular values of this projection is called an alcove. Alcove means, for example, here, 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 or here, 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 such region. We call them alcoves. So, as you know, there are many alcoves to which mu belongs. Recall that the multiple weight variety here is the inverse image of the projection divided by the action of T. So mu should be set in some of the alcoves, but there are many alcoves to which mu belongs. And if mu moves from one alcove to another alcove, the topological type or differential type of mu T changes, of course. But but they are birational, symplectically birational. Okay, so we have many alcoves, and consider mu in each alcove. There are many multiple weight variety we can get. But the next question is quite natural in this situation. So, are there any good alcoves? Which one is a good alcove? But it's a in some sense stupid question. But in this picture, the alcove containing 0 here might be interesting, or alcoves near the vertices here, 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 should be easy to treat. So, okay, the alcove containing 0 might be interesting, while alcoves near the vertices might be relatively easy. But if we restrict ourselves to the vertices near the vertices, there are still many such ones, if L is large. This is a picture for type A2, so L is 2. But in that case, the alcoves near the vertices, the number is 2. But if L is 3, there should be 7. And if L is 4, the number getting more and more large. So, to see this, the neighborhood of the vertex lambda 1 plus lambda n looks like this picture with negative sign. This should be the vertices here, and in this direction with negative sign of simple roots, the edge go out. Okay, and here is the definition. An open cone in the subdivision given by walls of the cone generated by alpha i's is called a chamber. Chamber is a cone generated by so open cone in the subdivision of the cone generated by alpha i's. For example, this is a picture of A3, SU4, and alpha 1, alpha 2, alpha 3 is the simple weight, and the chamber here means that the cone of this region or of this region this summing up 7 chambers in type A3. Among them, the open cone written by this form is called the nice chamber. In this case of type A3, the nice chamber corresponds to the cone of this region, alpha 1 plus alpha 2, alpha 1 plus alpha 2 plus alpha 3, and consider the cone of this region. This is a nice chamber. And suppose to consider our multiplicity varieties, I assume that mu is satisfies the following 2 conditions. Namely, mu is very close to the vertex lambda 1 plus lambda n, and the vertex minus mu is in the nice chamber defined above. In that case, mu is said to be special or extremely special. In the previous example, here, the special mu sits in here or here or here because the vertex lambda 1 plus lambda 2 is here, and near this region, in the neighborhood of this one, this minus mu becomes in the nice chamber, which should be here or here or here. If this is the case, if mu is special, our multiplicity variety, multiple weight variety becomes relatively simple as follows. So next is the theorem of this talk. So let G is SUL plus 1 of type L, and suppose lambda 1, lambda 2, and lambda n is in the interior of the wide chamber, and suppose mu is special, defined above. In that case, we write our variety MT as MLN because the different type of MT is determined by this L and N. So we write MT as MLN. Then we have the following. First, this variety MLN is a tower, has the structure of a tower of projective bundles like this. First, the base space is Pn-1, and the fiber is P2n-1. Next, this bundle is a base, and the fiber is P3n-1, and so on. The final fiber is P to the Ln-1. MLN has this structure. And second, the homology ring of MLN is described in this fashion. A polynomial ring of L generators of degree 2 divided by this ideal. And third, if we write the vertex minus mu as in this form of the combination of positive roots, then symplectic volume of MLN is given by the coefficient of this term in the expansion of this rational function of y1 to yl, where the number d here is a number defined by this formula, and in this expansion, Taylor expansion, we assume that this condition. Okay, so if you expand this rational function to power series of yi's, then take the coefficient of this term, we get the volume of MLN. And from this, we can derive the similar formula for the intersection pairings, because recall that the volume of ML, symplectic volume was a generated function of the intersection pairing like this. So we can get similar formulas from this. Finally, the ideal appearing here in 2 corresponds to a system of differential equations satisfied by this volume, which is considered as a function of parameter Q1 and QL. Actually, this is a polynomial of Q1 and QL, and which satisfies some system of differential equations. And the statement 4 means that the ideal generators of this ideal correspond to such differential equations. Okay, this is a theorem, and here is an outline of the proof. The statement 1 and 2 actually follows from the arguments in Gilman-Lerman-Sternberg in 1996 or Fu in 1992. In fact, this is a point, there is a complex vector bundle E, which is a direct sum of several line bundles, the sum of line bundles over ML-1n, which is a multiple weight variety for AL-1. On the other hand, MLn is a multiple weight variety for AL, and base is this one, L-1n, ML-1n. Anyway, E is the sum of line bundles over this guy, such that our MLn is a project bundle associated to E. This is a key point to prove 1 and 2. Oh, sorry. Here, this structure comes from the statement I just told you, and the ring structure here also comes from this description. To see the third statement, here, the volume formula, like this. To see this, it is quite natural also to use the theory of vector partition functions, which will be the next topic of this talk. Okay. So, but finally, next here, I want to mention that our MLn, the multiple weight variety of a special kind, is in fact a toric manifold associated to a certain polytope defined below. Okay. So I have to explain the notion of vector partition function and volume function, but very quickly, let me explain that. So delta, denoted by delta, a sequence of vectors in a lattice in RD contained in an open space. But anyway, the typical example is that delta is a set of positive roots of type AL or BL or something root system. And if we have lambda in the lattice generated by alpha i's, and the coefficients, if the coefficients are non-negative, we can define the following numbers, p delta of lambda, which is the number of ways to express lambda, given lambda, as a linear combination of alpha 1 and alpha n with coefficients in non-negative integers. The number of ways to express lambda in this form is the definition of a p delta of lambda, and this is called a vector partition function. And it is quite easy. Generating function of this partition function is quite very simple. And actually, generating function means this sum, and it is written in the product of power series like this. And as an analog, given y in Rn and m in Zn, define p delta lambda by m by this identity. A little bit complicated, but the similar structure it has. And it is also called a vector partition function, and the integers m and mi appeared as a power called weights or multiplicities. And next, I want to introduce the notion of partition polytope. So, given H in the positive cone generated by alpha i's, then we define x delta of H be the set of elements in this quadrant defined by this equation. This is called a partition polytope associated delta and H. And it is quite easy to see that it is compact, and our p delta of lambda partition function is the number of lattice points of this partition polytope, and p delta lambda by m is the sum of values of a function like this over the lattice points in the partition polytope. And vector partition, we defined vector partition function, but volume function associated to the vector partition function is the continuous analog of that. So V delta of H is just the volume of the partition polytope, the integral of 1 over the partition polytope, and some variants, V delta of Hm or V delta of H by m is defined the integration of some functions like this over the partition polytopes. This is some details, so I omit here. So, the vector partition function I defined p delta of lambda or volume function V delta of H is another formulation of the number of the lattice points in a complex polytope or the volume of a complex polytope. And tensor product multiplicity I defined in section 3 at that time Qg of lambda or Vg of lambda, etc. Are written by vector partition functions or volume functions like this. Final remark is that the volume function of this form, but the integral of this function is closely related to the generalized hypergeometric function due to Aumont and Gelfand. Okay, so there are 2 sheets left. So I want to explain some formulas for vector partition function or volume functions and its generalization. Here is the theorem of Brion and Vergne in 1997. They gave a formula for the case all the weights mi is 1, and they gave explicit formulas for this partition function, volume function, and another volume function like this form. But I don't want to go into the details of the notations, but only I want to do is to give you some remarks. So we can regard this explicit formula as equivalent Riemann-Roch theorem for a toric manifold associated to the partition polytope. Actually, the set appearing here, B delta of gamma, correspond to the set of vertices of the partition polytope. So this formula has geometric meaning. On the other hand, their proof is completely combinatorial. This is a remark. And here is a generalization. Here is a theorem by myself. There are similar formulas for partition function, volume function, like this, for general weights m, m1 and mn. Even if some of mj, mi are negative. But I don't write down this formula. It's a little bit long. I omit here, but it's a generalization of the formula like this by Brion-Vergne. We can get the formula with multiplicity. And as a corollary of this formula, we have the following theorem for the case that delta is type AL, the root system, positive root system of type AL, and H appeared here is in the ninth chamber. In that case, we have the following expression for the volume function VAL of Hn. N means that all the multiplicity, all the weights are n. And this is described by in this fashion, as I told you before, in section 3. And this volume function satisfies this differential equation, system of differential equations like this. And it turns out to become an ideal of the homology ring of MT. Anyway, using these, we obtain the formulas for the symplectic volume and the intersection pairings of the weight variety of special kind in section 4. And finally, I mentioned that this expression of volume function, similar formula to this one was also given by Brion-Vergne in 2006. Okay, that's what I wanted to talk about. Thank you very much.